13,000 feet, still 330 knots. We're doing pretty good. Okay, now here comes a crossover. I'm going in the afterburner. And what we do is pump up on the other side. You feel the acceleration there. There we go. Picture the belly of the airplane there.
Hi, I'm General Jack Daly, the director of the National Air and Space Museum here on the Mall in Washington, D.C. This museum is the home for the National Collection on Aviation and Space Artifacts, and examples of the aircraft that we have on display here are the Wright Flyer, which was the first heavier-than-air powered aircraft, and of course was flown by the Wright brothers in December of 1903 at Kitty Hawk, North Carolina. We have the Spirit of St. Louis, which was piloted by Charles Lindbergh on the first solo flight from New York City to Paris and made the first solo Atlantic crossing. We have the Lockheed Vega, flown by Amelia Earhart as the first woman to fly across the Atlantic. We have the Bell X-1, which was the first aircraft to fly faster than the speed of sound and was piloted by Chuck Yeager. We have the SR-71, which is the fastest operational aircraft in the world, and the X-15, which is the fastest rocket aircraft in the world. We also have the Space Shuttle Enterprise. The thing about these aircraft is that the technology developments in the first 97 years of flight have just been absolutely amazing. If you consider that the Wright brothers flew at about 18 miles an hour, Charles Lindbergh flew at about 145 miles an hour, Amelia Earhart flew at about 165 miles an hour, and then Chuck Yeager in the Bell X-1 went 800 miles an hour. The SR-71 is about a 2,000 mile an hour airplane, the X-15 a 4,500 mile an hour airplane, and the Space Shuttle 17,500 miles an hour. So you can see the incredible developments that have been made in aviation over these past 97 years. We have a very exciting program for you here today, and it's made possible through the sponsorship of the Best Buy Corporation. And we have Susan Hoff from Best Buy here to tell us a little more about today's program. Welcome, Susan. It's glad to have you. Okay.
Hi, I'm Susan Hoff, president of Best Buy Children's Foundation. Best Buy is pleased once again to sponsor the Insight Distance Learning program, now in its second year. Best Buy prides itself at being at the intersection of technology and life. We sell products that make people's lives better and more fun. And we also provide opportunities for children to be a little bigger part of the internet and learn more about technology. Today I have a couple of friends with me today. This is Nikki. Nikki is from Iowa City, and Nikki is sending a project up to the moon. Nikki, can you tell us a little bit about your project?
Okay, well, our project is going up on the shuttle in June 2001, and what we're doing is we're taking different types of media and putting different images on them, and we're going to send them up and see what effect cosmic rays have on them.
Nikki, do you want to tell them what school you go to in Iowa?
I go to Regina Middle School.
I've also got Nikolai here, who's got a favorite demonstration that he'll be showing you a little later in the broadcast. Nikolai, why don't you tell us about your demonstration?
Our demonstration is our project is our principles of flight, which are thrust, lift, drag, and weight. My favorite demonstration is a rocket balloon that shows the principle of thrust.
Can you tell us what school you go to in New York?
The school I go to is Woodlawn Elementary School.
Thank you. We're pretty excited about this program, and as you can see, we've got a lot planned for you today. The kids are very excited to show you your demonstrations, and you'll be coming up soon with that. Now I'd like to teach you a little bit more about General Daly. General Daly has a wide and varied career in aerospace. He's flown many different planes and has also been part of NASA. General?
Thanks, Susan. I've been a pilot for over 40 years, and I can't think of a more exciting or interesting profession. The reason I say that is because there are no two flights that are ever the same. There's always something different, whether it's the air temperature, the crosswinds, the weather, or the performance of the aircraft. I think that's what makes it exciting, makes it interesting. You also have to be planning ahead. You can't ever assume that everything is going to be the same as it was the last time you flew, and that's what keeps it interesting and always changing for you. I've flown a great number of airplanes, and I've liked each one of them. And here's an example of the A-4 Skyhawk, which is an attack aircraft that I flew back in the 1960s. This is the F-4 Phantom. It's a fighter, first Mach 2 aircraft that we had in the inventory. This is the F-8 Crusader, another fighter. And the SR-71, which I mentioned earlier. This is the world's fastest operational aircraft, and I had a chance to fly it while I was in NASA. That aircraft set the transcontinental speed record by flying from Los Angeles to Washington, D.C. in 68 minutes. But if you put it in terms that are easier to understand, if you saw the movie Dirty Harry, when Clint Eastwood held up that pistol and he said, "This is the most powerful handgun in the world, the .44 Magnum," that airplane flies 2.5 times faster than that bullet. So you can see what I mean. It's exciting technology that we've experienced over this period of time. And even though the basic principles of flight are the same, each aircraft has its own personality, and you need to learn those characteristics in order to get the maximum performance out of the aircraft. To hear more about these basic principles of flight, let's switch over to Blake Reed down in our How Things Fly gallery. Blake?
All right, thanks a lot, General Daly. We really appreciate it. Just so you know, we are live, which means that if you ever see an email come up on your screen or a 1-800 number, it means you can call it. Might as well call that 1-800 number. It's free. No reason not to. You can write that email address. Give us email's free. Why not? Might as well do it. Send us your questions. Throughout the show, we'll be taking your questions, and we'll be going into, and hopefully you'll help drive the show, because we've got a lot of stuff to do, right? And the first thing we're going to do is we're going to meet some kids from Schenectady, students from Schenectady, who've got a little something to show us, a little teaser. What are your names? Tell the audience.
Shelly. Rachel.
All right, so we've got Shelly and Rachel. All right, what are you going to do for us?
We're going to show you how to get one cup out of another cup.
So you're going to show us how to get one cup out of another cup. Well, I know how to do that. This is how you do it, right?
No.
So you got a different way. All right, well, why don't you show me?
Okay.
Yeah. Oh, well, so it looked like you blew, right? Well, let's see that again, right? All right, now for everybody watching this, all right, remember this trick. We're going to come back to this trick a little bit later, all right? I'm going to put these in my pocket, right? And right now, let's take a phone call, all right? I got a phone call. Who's on the line? All right, Duran from New York. What is your question?
Hi.
Hi, how are you doing?
Good.
Good. Tell me, what's your question?
How fast can a plane fly?
How what?
How fast can a plane fly?
How fast do you think they fly? Oh, well, see, you don't know, do you? Well, it really depends. Like, really, planes can fly as fast as you push them, but the top limit, right, is really, I think it's about like Mach 15, something like that. You know, they don't really get much faster than that. Usually, you know, supersonic airplanes fly faster than Mach 1. 1 Mach is the speed of sound. And the speed of sound, depending on where you are, it's about 700 miles per hour. So you can fly a lot faster than Mach 1. People, yeah. Oh, so I hope that answered your question, right? We got another question, right, from Julianne from Florida. Did I say your name right?
Yeah.
Yeah? All right, what's your question?
My question was, why don't planes melt when they move the speed of sound?
Why don't planes melt when they reach the speed of sound? Oh, my goodness. That is very technical. I'll tell you what we're going to do. we are going to hold on that, and we're going to answer that question a little bit later in the show. All right? Think about that, because we are going to talk just a little bit about supersonic flight. All right, so that's what we've got. We've got this trick. I've got these cups. We're going to come back to this, right, just so you know a little bit about what we're doing this hour. Thanks for your questions. Keep them rolling in, right? Also, one of the things that you may have done already in your classroom is measured the weight of the air in your classroom. If you've done that and you have the answer, give us a call, and we'll compare. We'll do a little comparison between your classroom and the How Things Fly Gallery at the National Air and Space Museum. Now, let me introduce you to Dr. Ann Spence, who's going to tell you a little bit about the rest of the field trip. Ann?
Wow, did you see that cool cup demo they did out there? That's just the kind of stuff we're going to be doing all through the show today, where we're going to learn about all the kinds of things that impact flight. I'm Dr. Ann Spence, and I'm a visiting professor of aerospace engineering at the University of Maryland, and I started learning about how things fly when I was 2 years old. I've been flying with my dad ever since, and it's been a great time. I always knew that I wanted to be involved with aerospace engineering all the way through elementary, middle school, and high school, and I finally got the chance to do it. I graduated with a degree in aerospace engineering and even worked at Bell Helicopter. I've gotten to do all sorts of incredible things. Not only am I an aerospace engineer, but I'm a mom and I'm also a wife. So you can do everything you want to do. But today we're going to learn about all the different kinds of forces that are acting on aircraft. We're going to learn about how air involves itself with aircraft. If you look down at the bottom of your screen, you're going to see our 800 number and the email address where you can email your questions or call your questions in live, and we're going to try to answer them the best we can. So make sure you put your thinking caps in and call in some questions, because right now we're going to learn a little bit about air. So let's blast off to Blake.
Thanks, Ann. All right, we are back here. We got a couple more students, right? Tell everybody what your names are.
Corey. Annarisa.
All right, so we got Corey and Annarisa here. What we're going to do is, like Ann told you, we're going to learn a little bit about air. How do we know air exists? If you don't believe me, do this. Stick your hand up in front of your face. Wave at yourself. Feel that? Well, you can't feel it unless you do it in your classroom, right? But you feel something, so you know air's around us. Well, what does that mean? What we are going to do is we are going to figure out what that means. First thing I got a trick. You guys want to see a trick?
Sure.
All right, you can do this trick at home. A lot of these things that we do, they're not magic tricks, they're science tricks, and you need some really simple things. First, you need a cup, then you need some water. All right, here's how we know it's water. You want to hear a joke?
Yeah.
Yeah, knock, knock.
Who's there?
John.
John who?
John the Baptist. Yeah? All right, try that. Okay, here we go. Then you need a card. Take your card, stick it over the top of your cup, flip your cup over, right? Take your hand away, and what? Oh! What held it on there for a little bit?
Air.
Air, right. And then eventually gravity took over, right? There's obviously gravity in this room. All right, so let's do another one.
Okay, we're going to do an experiment called the paper wad.
You're going to do an experiment called the paper wad, all right? And for this experiment, for this trick, for this demonstration, you will need a jar, 2-liter bottle, and you will need a wad of paper in the mouth. All right, before you do it, all right, tell us what you're going to try to do.
I'm going to try to blow the paper wad inside this.
You are going to try to blow the paper wad inside the bottle. Everybody watching this in your classrooms, take a vote. You think you can do it? Stick your hand up, all right? If you think you can't, stick your hand up now. All right, now let's try it. See what happens. Give it a go. Oh! So you can't blow it in. No, try it again. Oh, so you can't, well, why can't you blow it in?
Air pressure.
Air pressure. What's inside your bottle right now?
Air.
Air. There's a lot of air inside the bottle, right? So it's like you're trying to blow this paper wad into something, right? Well, you know, it hits that something and it bounces back out. It happens very quickly. You want to do another one?
Yep.
Yeah, let's do another one. All right, what else we got? Here, I'll take this.
The napkin dunk.
Yeah, okay, let's do it.
Now we put a piece of napkin inside of a cup, and the whole objective is to see if the napkin will get wet when we put the cup inside the water.
All right, so the napkin is crumpled up inside the cup. Turn the cup upside down so the napkin can't fall out. Dunk it in this tank of water, right? Water. Now pull it out. Now, do you think the napkin's wet? Let's try it and see. Pull it out. Ladies and gentlemen, this is not a trick. This is real science. All right, unfold it, show everybody, and you will see that this napkin is, in fact, still dry. Why do all these things work the way they do?
Because air takes up space.
Because air takes up space. That's one property of air, right? Wherever you have air, it has to take up some space, right? And we just showed that with all these things. Thank you guys very much, right? Have a good day, right? Let's get some more people in here. All right, who's next? What are your guys' names?
Kanisha.
Kanisha?
Gayatri.
Gayatri. All right, so what are we going to do?
We're going to do an experiment to show that air has more properties.
So we're going to do a little something to show that air has more properties other than just taking up space. All right, so what we got right behind me, right, we've got this balance beam. Let's move around behind the table. All right, now what is this designed to show? You guys tell me.
That the two balloons weigh the same amount.
Okay, that the two balloons are balanced. What's inside these balloons right now?
Air.
Air. All right, so there's some air in this one. There's some air in this one. All right, now it's a little bit balanced. Here's what we do. We take it, we let all the air out of one balloon, and what happens?
It becomes unbalanced.
It becomes unbalanced. What unbalances it?
That this one doesn't have any air and that one still has air
That
in
one
it.
doesn't have any air in it anymore, right? This one still has a lot of air in it, so it still has weight. Now the extra weight pulls the side of this balance down. All right, so this is what we've learned so far. Air has mass, and air takes up space. Now we got a couple of phone calls. Let's take a phone call from Courtney from New York. How you doing, Courtney?
I have a question.
Yeah, what's your question?
How does the airplane fly with all the people in it?
How does an airplane fly with all the people in it? All right, well, what do you think? What do you think?
I don't know.
You don't know? That's very honest of you, all right? Well, really, it's like this is what we're going to get into a little bit later in the show. We're going to get into what are called forces of flight. If you get enough of a force to lift up airplanes, then, well, you can put a whole lot of weight inside the airplane, and it'll keep flying. Does that a sort of answer your question? Yeah, all right. Well, now what we've got Sean from Indiana. Sean, what's your question?
My question is, what is the smallest airplane in the world and how fast does it go?
Your question is, what is the smallest airplane in the world and how fast does it go? All right. Now, this is a trick question, I know, because the smallest airplane in the world is probably whatever you can make with a small piece of paper. It's still an airplane, right? If you're asking me what's the smallest, like, real metal airplane in the world, I don't know that, but why don't you make a really tiny paper airplane, and that'll be the smallest that, well, you'll ever seen. All right, now what we got, well, let's get some more people in here, right? And let's do the rest of this. All right, now what we've learned so far is we learned that air takes up space, and then we learned that air has mass. Now what we're going to learn is that, well, all that has to mean something, and what it means is pressure. So to explain what pressure is, I've got Chris Ludwig here, who is an explainer at the museum, and a couple more students, and they're going to go all into pressures. So take it away, Chris.
Okay, what we're going to do is we're going to do a little experiment to show how air pressure works. But first, I'm going to have my assistants introduce themselves.
My name is Taylor. And I'm Shakeba.
Okay, I got a question for you two. Do you guys think that air is strong, or do you think it's weak?
We think it's weak.
Think it's weak? Okay. What I'm going to do is I'm going to ask Shakeba to take these two hemispheres, and I'm asking her to inspect them, make sure there's nothing suspicious about them. Because what I'm going to do is I'm going to put them together. Nothing on it. Okay, I'm going to take this part, and I'm just going to put this rubber piece in between them. I'm going to give this hemisphere one big twist, and I'm going to ask Shakeba to pull off the top. Okay. And that was pretty easy, right? Okay, what this shows is, for every square inch of surface area, you have 15 pounds of air pressure pushing down on that surface. So about an area this big on your body, you have 15 pounds of air pressure pushing down on you. The reason you don't feel this air pressure is the reason why most people think that air is pretty weak. It's because you have air on the outside, but you also have air on the inside of your body, just like these hemispheres. So the air on the outside is pushing in, but the air on the inside is pushing out. So they cancel each other out, therefore you don't feel this pressure on your body. What I'm going to do is I'm going to take most of the air out of these hemispheres by putting this hand pump on. And I'm going to try to pump most of the air out. This takes a little while.
All right, well, Chris takes all that air out because it does take a while. He's got to do a lot of pumping. He's a big guy, but it still takes him a little while. Let's answer a question. We got a question from Scott, right? Scott, where are you from? Scott from Florida. Oh, there you are. Hey, Scott from Florida. What's your question?
Okay. Okay, we're having a little bit of gun shyness here.
Somebody's
the
a little
question
shy.
is,
Okay.
say the question. The student wants to know why in a skydiver there is smoke coming out of the back.
Why is there smoke coming out of the back when
In
you
a-
see a
in a
skydiver?
plane
I know what
that,
you're talking about, yeah. Well,
You know, that writes on in the sky?
yeah.
What do they put in their exhaust to make it be red?
Huh. I don't know. Right? But the answer to your first question is, why do you do it? Well, so you know where you are, right?
Yes.
Yeah, there you go. All right, let's go back to Chris. I think he's finished pumping out all the air from inside this Magnebrick sphere.
Okay, most of the air is out right now. And all I'm going to do is I'm going to ask Taylor here to try to pull off the top. And on the count of 3, he's going to pull as hard as he can, okay? 1, 2, 3. Okay, as you can see, this time it's a little harder to pull off the top. The reason for this is when you take the air out of the center of these hemispheres, you're also taking away the air pressure. So all you have is 15 pounds per square inch pushing these two hemispheres together. You don't have the air on the inside pushing out anymore. So if you do the math, that's about 200 to 300 pounds of pressure pushing these two hemispheres together. So no matter how big and strong he grows up to be, he probably will never be able to pull these hemispheres apart unless I do what?
Put the air back in.
Okay, I'm going to let the air back in. And as you can see, he has a much easier time this time. So that pretty much shows how strong air is, and we're going to let Blake take it from here.
All right, thanks a lot, Chris. So what do we learn? We learned that air has mass. That's one thing. Another thing is that air takes up space. You can't squeeze it. And all that means, like air is so powerful, it exerts a lot of pressure. There is so much air inside this room that I'm in right now. It weighs as much as this brick wall behind me. That's a lot of weight. If you added up all the air in your classroom, it would probably weigh about 500 pounds, which is about 4 of me, just about. All right, hey, let's take a quick email question. We got one from Courtney at Woodlawn School in Schenectady, New York. Right, Courtney, your question is, what's the longest distance an airplane has flown? And the answer to that is all the way around the world. I assume you meant once. We do have an airplane here in the museum called the Voyager. It flew around the world on 1 tank of gas. So figure out how long it is around the world, and you've got your answer. All right, now let's go to Dr. Ann Spitz. We're going to learn a little bit more about forces of flight.
Thanks, Blake. But before we get to the forces of flight, I got a couple of phone calls coming in, so let's take our call from Motina out in Arizona. What do you have to say? Motina?
How fast can gliders fly?
How fast do gliders fly? Is that your question?
Yeah.
Okay, gliders fly pretty slowly, actually. All they fly on is they have to be pulled into the air by some other aircraft or launched somehow because they don't have an engine to get up speed. So they can fly pretty slowly. I would say probably as slowly as 40 miles an hour, maybe up to 100 miles an hour. It just kind of depends. Okay, thanks. We got another phone call coming in from Andre in California. Andre, what's your question?
My question was, what kind of air was in them balloons? Was it helium or human air to show that weight?
What kind of air do you think was in the balloons?
I would have to say helium.
No, it was regular air was in those balloons.
Oh,
Regular air. That's pretty cool, huh? Now I've got a couple of emails here too. I've got an email from Marcino who wants to know what speed does the plane need to go on the runway to take off. Now that's a really good question, but you know what? It depends on the airplane. Some airplanes take off slow and some airplanes take off fast. This Cessna back here takes off pretty slowly, but some of the commercial aircraft have to take off a lot faster to get enough lift on their wings. I've also got another question from Ryan in Schenectady, New York. He wants to know, how can a plane fly if the wings on the top and bottom are equally curved or flat? You must have been doing your work and researching your aerodynamics, because this is a very good question. That's called a symmetric airfoil section, and what you have to do for that kind of airfoil is make sure you have it at an angle of attack, like this. It can't fly just like this, because then you've got the same amount of pressure on the top and the bottom. So you've got to can it a little bit like this to get it to flow over. And then there's another question which is kind of related to that, and it's from Mrs. Campbell's class at Woodlawn School in Schenectady. How does an upside-down plane stay in the air? Well, it's the same kind of thing. If you get enough angle of attack on your airplane, it's going to stay in the air because it's going to generate enough lift. So you kind of got to be flying upside down and at an angle in order to stay up in the air. So let's talk a little bit more here about the forces of flight. We talked about kind of how air weighs something and we weigh something. So we have weight pulling down on us. Then we're going to have something to overcome that weight, and that's going to be the lift. We're going to have drag, which is pulling us back, and we're going to have thrust, which is trying to push us forward. So let's do a little demo here. What are we going to do with this today?
We're going to take a hairdryer and put it across the top of the wing and see if it creates lift.
See if it creates lift. All right, let's turn that hairdryer on and see what happens. Look at that! Isn't that awesome? All she's doing is blowing air over that wing section, and we're getting lift. Lift just by blowing air over it. But how does that really work? I don't know. You know who the guy is for this question? Blake. Let's send it off to Blake.
That's a good question, Ann. Thanks for asking it. How does a wing get a lift? Just by blowing air over the top of it. What we're going to do is now we're into the forces of flight. And we're going to show you a couple of quick animations because forces really point in different directions. And on any airplane, there are 4 forces of flight. What we are doing right now is the force of flight called lift. Lift is the force that, lifts up an airplane. So if an airplane's moving fast enough through the air, right, then you get a lot more lift. See, there it goes, right? So lift pulls up, and then things that go up have to come down because of the second force of flight. Now we got the last force, drag, and then we got thrust. We'll do those later, right? But right now, let's concentrate on lift and weight. Now, to understand lift, we do need to understand something called the Venturi effect. Now, the Venturi effect has to do with getting a lot of fluid through a little squeezed space. So let me show you a little video of a kayaker made by some of the students in Schenectady, New York. All right, now here's what happens. All right, now a lot of fluid, right, when they bring it up, a lot of fluid comes through, there it goes, comes through, and it gets squeezed through a little narrow opening. Now all that water from the top that's spread out gets squeezed, and it pulls that kayaker through very quickly. Watch, blah, blah, blah. There it goes, right? Speeds right through that. Here we go. Here it comes again, right? That's the Venturi effect. All that water squeezes through a little narrow opening, right? And when it squeezes through, it speeds up. The same thing happens with air because air and water are what we call fluids. They are not liquids, but they are fluids. Right, so we got the Venturi effect. Now, how does that affect flight? Well, Venturi leads us to the next thing, the Bernoulli principle. Daniel Bernoulli is a friend of mine, right? So what we got is we're going to show a couple of his experiments to show what happens when air speeds up after it's constricted. I've got with me, who have I got? What's your name?
Nikolai.
Nikolai?
Shelly.
Shelly. I got Nikolai and Shelly. Tell me what you're going to do.
We're going to take 2 balloons and we're going to blow through it and see what's going to happen.
So you're going to take 2 balloons, you're going to blow in between them and see what's going to happen. Now for everybody watching in your schools, what do you think is going to happen? Do you think they're going to move apart or together? It's one of those. I'm not going to tell you. Let's take a quick vote. Who thinks apart? Who thinks together? Who voted twice? Yeah, shame on you. All right, now let's try it, see what happens. Do it one more time. So when you blew, what happened to them?
It went together.
They moved together, right? Because faster moving air in between the balloons has less pressure. That is Bernoulli's principle. Faster moving air has less pressure. Let's look at another one. What else you got?
We have a hairdryer and a ping pong ball.
You have a hairdryer and a ping pong ball. All right, so turn on the hairdryer. Right? Then you got your ping pong ball. Now you may be thinking, big deal, right? Because, well, what's holding it up? Just the air. But why doesn't the air just blow it away? What we've got is we've got a cocoon of air. This ball is inside a little cocoon. Hold it very still. Let me see if this works. You could actually dribble it a little bit. Poke, 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 right? And it's stuck. All of the high pressure air on the outside pushes it back in. All right, so this is Bernoulli's principle. Let's go back to our cup from the beginning of the show. Remember these cups, right? Blow across the top. Then we have faster moving air over the top. Then we have less pressure over the top. Less pressure over the top, higher pressure under here. So let's see what happens. The higher pressure in between the cups pushes that cup out. All right, so let's go to Dr. Ann Spence and see what happens.
What is this? How is this actually happening, and how does it affect flying? Let's say you take a section of our wing up here. This is what it would look like if we cut a section out. Now, when we blow the air over this surface, remember, when the Venturi effect, it got smaller. And what happens when we get a smaller thing? Our wind goes faster over the top. And when our wind goes faster, what does Dan Bernoulli tell us? He says the pressure goes down. So that means we have lower pressure here, higher pressure here, and what does it do? It lifts the aircraft, it lifts the wing section up in the air. So I think do we have a phone call today? Do we have a phone call today? Okay, our phone call is from Matthew in Indiana. Matthew, what's your question?
What's the barrier of sound?
What's the barrier of sound? Well, the sound barrier is when we pass through Mach 1. Is there anything else you want to know about that?
No, thank you.
Okay. Samantha from Florida, do you have a question for us today?
Yes, I do.
What's your question?
After a space shuttle takes off, what creates the sonic boom?
Well, as the spacecraft goes faster and faster and it crosses through that barrier at Mach 1, then that's when you hear the sonic boom. It's when a shock wave forms and moves across. Okay, does that answer your question? All right. We have another question from Adam from New York. Adam, what's your question?
Hi, what is the materials of a body of the airplane?
What is the what? I'm sorry, could you repeat your question?
What are the materials of the body of the airplane?
Okay, what are the materials that the aircraft is made out of? Well, it can be made out of a lot of things. Some of the older aircraft are made out of fabric and wood. Some of the newer aircraft are made out of metal, and some even newer ones are made out of different kinds of plastics and things like that. So they're made out of all sorts of different stuff. Okay, we have one more phone call from Joe in California. Joe, what's your question?
Hi, Doctor.
Hi.
For a helicopter to gain lift, do you increase the main rotor speed and also the pitch?
Right, you really don't have to increase the main rotor speed. Once you get it up to speed, it's fine. But what you have to do is increase the pitch on each of the blades so it's seeing a higher angle of attack, which gives you more lift, and that lets you go up in the air. Okay, Tony from Massachusetts, do you have a question today?
Yes, I do. What's the difference between, I know the difference between a turbofan and a turbojet, but usually when you're dealing with a turbofan or a turbojet, which engine operates better at a higher altitude?
Well, now that's a good question. I don't know. Let's pass that over to John Anderson and see if he can field this one.
Okay, which type of engine, a turbofan or a turbojet, performs better at higher altitudes? Well, the answer is they both perform about equally well at higher altitudes. The thrust of those engines drop off with the density of the air, which drops off with altitude. So a turbofan or a turbojet do not necessarily have features that make one better than the other at higher altitudes.
Now we're back over here at the Cessna, and I want to talk to you a little bit about how you actually control an airplane once you get it up in the air. Let's say that we wanted to maneuver a little and say we wanted to move right. Let's talk to Gayatri up here and see. Gayatri, if we wanted to roll to the right, what would you do?
I would turn the steering wheel to the right.
Right, do that and see what happens. See, when Gayatri turned the steering wheel to the right, look what happened to this aileron. It came down. And you know what that does? It makes the wind go faster over the top of the over the wing, which increases the lift on this wing. But on the other side, what you don't see is that the other aileron is moving up, and it's decreasing the lift on that side. So when the lift increases on this side and decreases on that side, what you see is your airplane rolling to the side. Now, we also have similar controls in the back called the elevator, which allow us to pitch down and to pitch up. A lot of these control issues are things that were first developed way back when the Wright brothers first started flying. So we're going to pop over to John Anderson and talk about, nope, before we go there, we're going to do a phone call. Kevin, what's your question?
Yes, I'd like to know if you could tell me why Charles Lindbergh made the flight to Paris.
Well, that's a good question. I think John, our historian, is a good person to answer that. John?
We're going to talk about Charles Lindbergh in a few minutes. We'll just pass on that. And instead, what we're going to do is talk more about lift. First of all, I have a question for the students here. What part of the airplane is the main part that produces lift?
Wings.
The wings, of course. And you know, the Wright brothers knew that. As a matter of fact, I have here a model of the Wright Flyer. The Wright brothers knew that. They had not only one wing, they had two wings. This is called a biplane, and is braced. The two wings are braced by struts and wires in between. This is what we call a strut and wire biplane. Now, another question for you. If you were building this wing, would you build it out of something solid and heavy like lead? Would you build a lead wing? What do you think? No, why not? Why not? Too heavy. What would you use to build? What would you want to build the wing out of? Yeah, okay, boy, these people know it. A lightweight, strong structure. And you can see on your video right now that some pictures of the Wright Flyer that is hanging here in the National Air and Space Museum. It's the real Wright Flyer, not a model like I had in my hands. And you can see the wings, you can see the two wings, you can see the pilot lying prone on the wings, and so forth. Now, there's something important that I want to share with you, and that is the fact that what's important aerodynamically is the lift-to-drag ratio. That is, for the Wright Flyer, the ratio of lift to drag is typically like 5. That means that for every pound of drag you encounter, you're getting 5 pounds of lift. And that's a pretty good advantage. That you're getting a lot for your money there. Now, I have a question here which reflects on this. We had a question from Brian Noel at Woodlawn Elementary in Schenectady. He asked, what is the difference between the way an airplane flies and the way the space shuttle flies? And the answer is in this lift-to-drag ratio. The space shuttle was designed just to glide back through the atmosphere, slow down, and land. You want high drag for that. And so the space shuttle had a low lift or drag ratio of about 3 or so, whereas a real airplane that's designed to fly efficiently through the air has a much higher lift to drag ratio. That's the difference between an ordinary airplane and the space shuttle. Both of them fly, but the space shuttle flies inefficiently, intentionally so it'll slow down as it comes back in the atmosphere. We have a phone call from Megan in Florida. Yes, Megan. Okay. Well, we'll move on to a phone call from James in California. James, are you there?
Yeah.
Okay. What is your question? You're not coming through, James. What is your question? Well, Nathan from New York. Let's try your question. Gee, we have a lot of speechless people here today.
How high can planes fly?
How high can planes fly? Well, that's a good question. Ordinary airplanes like you would fly around on, airliners like a Boeing 747, will typically fly about maybe as high as 45,000 feet. Special airplanes like we have one in the Air and Space Museum, the X-15, which flew as high as almost 300,000 feet. It almost got up out of the atmosphere. We have another call from Tony in Massachusetts. Tony, are you there?
Yes, I am. My question is, on afterburning turbojets and turbofans, do they operate a little better at higher altitude or lower altitude? However, using traveling at supersonic speeds.
Well, there are two questions there. First of all, turbojets and turbofans operate equally well at higher altitudes as well as lower altitudes, although in terms of the fuel consumption, you want to fly jet airplanes at high altitudes where the drag is low in order to minimize the amount of fuel consumed. So we don't fly around at sea level in Boeing 747s. But in terms of the two kinds of engines, they operate equally well. Now, what was the other part of your question? Please remind me. Oh, the matter of the speed. If we are talking about an airplane to fly less than the speed of sound, turbofans are better because they have big fans. They're like propellers. For airplanes that fly at supersonic speeds, then we want turbojets. So we're talking about aspects of lift, and we also talked about drag. Let's talk more about drag, and for that we'll pass on to Blake.
Thanks a lot, Dr. John. Really appreciate it. So far, we've gone into two forces of flight, really. Well, first, we went into lift, and Dr. Ann told us a little bit about how airplanes get lift, the Bernoulli's principle. Then, you know, we sort of skipped over weight because everybody's familiar with weight. Things that go up have to come down because gravity gives things weight. The third force of flight is a big problem for airplanes, and it's called drag. So what we are going to do is show you this little graphic. See, airplanes fly forward, right? And they push against the air, and well, of course, the air pushes back. How do we get around it? To know a little bit more about drag, I got Chris Ludwig here, an explainer at the museum, and we are going to show you a little experiment. Take a look at this.
Okay, what we're going to do is we're going to do a little experiment to show you how drag works. Before we do that, I'm going to have my friends here introduce themselves.
I'm Chris.
I'm Chris.
I'm Nikolai.
Okay, we have Chris and Nikolai here. And what we're going to do is we're going to show you how air really works against the feather and causes drag. So when I turn this tube upside down, do you guys think this feather is going to fall slowly or fast?
Slowly.
I think slowly.
Okay, both of you said slowly. I'm turning it upside down. And as you can see, the feather does fall very slowly like they said. Do either one of you know why this feather's falling so slowly right now?
I know, because the feather has ripples in it, which act like a parachute and catch the air, which allows the feather to fall slowly.
And what he said was exactly right. What happens is if you've ever seen a feather, you know that it's spread out, and as it's falling through the air, air's getting underneath this feather and it's pushing on it. And this is what slows the feather down as it falls towards the earth. So guys, if I took all the air out of this tube and then turned this tube upside down, is the feather going to fall fast or slow now?
Fast.
Fast. Okay, all I'm going to do is I'm going to take my vacuum pump back here. Let me turn it on. And I'm going to suck all the air out of this tube, but this takes a little while. So.
All right, so while Chris is doing that, while he's sucking all the air out of the tube, let's take a few phone questions. All right, first we have Sunny from Florida. Sunny, what is your question?
Hello?
Hey, Sunny, how you doing? Hey,
what or how is the air in a tornado measured the capacity of?
All right, so really what your question is about tornadoes, right? Yeah, okay.
Yes, sir.
All right, so really what happens, we learned with the Bernoulli principle before, right? This is actually very applicable because we learned with the Bernoulli principle says faster moving air has less pressure. Does the air move pretty fast in a tornado? Yeah. So is there a lot of pressure or a little bit of pressure in a tornado? A little tiny bit, right? Because the air is moving so fast that there's not a lot of pressure. So a tornado is really a big pressure difference. A little bit of pressure in the tornado, a lot of pressure on the outside. And that really has to do with a lot of the tornado's destructive power. Thanks a lot. That's a really good question. We're going to go back to Chris, and then we're going to finish this up and take a couple more questions. Hold on.
Okay, most of the air should be out now. I'm just going to turn this valve and take off my vacuum pump. So all I want you guys to do is I want you to watch the feather when I turn this upside down. And as you can see, it falls very fast now, unlike the first time I turned this around. What happens is another name for drag is air resistance. When you take the air out of this tube, you're also taking away the resistance against the feather as it falls towards the ground. So what happens is when you have air in here, you have gravity pulling the feather down, but you have air pushing back up on it, slowing it down. Now what you have is you have no air on the inside, so the only thing that's acting on the feather is gravity, and that's pulling it down towards the ground. To show you that's not a trick, I'm going to let the air back in, and as you can see, the air is starting to push up against it again, and it's falling very slowly, and that's how drag works. And I'll let Blake take it over from here.
Thanks a lot, Chris. So as you can see, drag is a big problem for airplanes, right? Because the feather is just a little tiny thing, but an airplane is a big thing. Before we do a little bit more about drag, we do have another phone question from Megan in Florida. Hey, Megan, how are you doing?
Good.
Good. What's your question?
What is the newest plane in the National Air and Space Museum?
What is the newest plane in the National Air and Space Museum? I'll tell you what. we're going to do a little bit of research, and we'll get back to you. Is that acceptable? Good. All right. So we learned about 3 forces of flight so far. We learned about lift. We learned about weight, and then we learned about drag. We have another phone question. Who's our phone question from? Somebody in Florida. Who? Yeah. Andrew in Florida. There we go. Andrew in Florida. What is your question? Oh, Andrew, you're not in Florida. You're in New York. Hey, Andrew in New York. What is your question?
Why do planes have jet engines?
Why do planes have jet engines? That's a super question. Well, really the answer is people are impatient, right? You go to any big airport, right? What do you see? Do you see a lot of propeller airplanes? No, because propeller airplanes are too slow. People are in a hurry. So jet engines are a lot faster, which is why so many people ride them, because they're so fast. Get people where they're going quicker. That's really why airplanes have jet engines. All right, so we've learned about 3 forces of flight, right? We learned about lift, we learned about weight, and we learned about drag. To understand a little bit more about how drag affects airplanes, let's go back to Dr. Ann Spence to go a little bit more. Ann, how you doing?
Hey, Blake, thanks. It's about time, man. All these questions, we've been waiting. Let's talk about drag a little bit and look at these 2 aircraft that we have here. One of these aircraft has more drag than the other. Can you guess which one it is? Which one is it, ladies?
This one. That one has more drag than the other.
I think it's this one.
This one has more drag than this one. Now, why do you think that one has more drag?
Because of the size and shape.
Right, because it hits that front end and it goes, whoa, there's a lot of stuff in the way. I'm going to slow down a little bit. And then this one is nice and streamlined, so it doesn't have as much drag. I've got a really good question on email here from Sabrina at Woodlawn Elementary. And Sabrina says, do the pilots ever get scared when flying? Well, that's a good question. You know what? I've flown an airplane before, and yeah, there are some times I get scared because sometimes it'll throw something at you that you're not really sure you can handle. But usually the pilots are so well trained, they know exactly what to do. So they do kind of get scared sometimes. All right, so we talked a little bit about drag, and next we're going to talk about one of the aircraft that's really draggy looking, and that is the Spirit of St. Louis. Let's head over to John for the Spirit of St. Louis.
In May of 1927, Charles Lindbergh flew the Spirit of St. Louis all by himself across the Atlantic Ocean from New York to Paris. Here is a model of the Spirit of St. Louis. We had a question earlier as to why he did this. As we see him getting in the airplane, I'll answer that. Charles Lindbergh flew across the Atlantic Ocean by himself for 2 reasons. The challenge of it, to be the first to do that. And secondly, for the money, because there was a prize called the Orteig Prize for the first person to do that. That's why Lindbergh flew across the Atlantic. Now, think about this. You want to design an airplane to fly all the way across the Atlantic Ocean. What would you want to do? Anybody have an idea? What do you do to design the airplane to do that? You put a big gas tank, and there's a big gas tank in the middle of this airplane right behind the pilot, so you have lots of fuel. Also, what do? Would you design the airplane to have high drag or a low drag?
Low drag.
Low drag, of course. Again, we're back to this lift-to-drag ratio. As we look at the airplane on the video, the lift-to-drag ratio of the Spirit of St. Louis was more than 10, twice that of the Wright Flyer, and is a much more efficient airplane. If you look at the Spirit of St. Louis, you'll see a fairly streamlined airplane. We have a call from Kevin in New York. Kevin, what's your question?
What keeps an airplane in the Earth's atmosphere?
So what keeps the air what keeps the airplane in the atmosphere? Ah, okay. As you fly higher and higher, the atmospheric density gets lower and lower, and the lift gets lower and lower until the point the lift no longer equals the weight, and you can't fly any higher than that. And that's what keeps the airplane in the atmosphere. That's why it keeps it doesn't go zooming out of the atmosphere. One other thing, there was a question that we had, a question from Mrs. Campbell's class at Woodlawn School in Schenectady. Why do planes do loops, or how do planes do loops in the air? Lift is the answer. Take this airplane, suddenly increase the lift a lot larger than the weight, and the airplane is going to go up like this and over. So you simply increase the lift 2 or 3 or 4 times the weight, and the airplane will do a loop. That's the answer to that question. Now, Finally, we need to talk about thrust. To talk about thrust, we go back to Blake.
Thanks a lot, Dr. John. All right, we've gone through 3 of the 4 forces of flight already. We went through lift, we went through weight, we went through drag. There has to be some force of flight which pushes things forward. Let's show that animation, right, so you know which direction this force of flight glows. All right, yeah, there it is, right? See your little airplane, right? The force of flight that pushes, that thrusts that airplane forward, yeah, that's called thrust. Ooh, how creative, right? There are a lot of different ways of getting thrust. One way is with a rocket. So I'm back here with Shelly and Rachel. How you guys doing?
Good.
Good, right? We're going to do another activity, right? To show one way to get thrust. What are you going to do?
First, we're going to blow up this balloon and tape it to the bottom of the straw and let it go and see how far it goes.
So we are going to blow up the balloon, tape it to the straw, see how far it goes after we let go. Now, it should be important. This is a rocket. This is a real rocket. This is not, it's no big fancy rocket made out of metal with a lot of explosions and a lot of heat. Nothing like that, but it is real. It follows the same principles. Because really, you have a lot of fuel on the inside, all the air you blow in it, and it all comes out one exit, just like a rocket. So let's do it. All right, blow up that balloon. Yeah. All right, so you're filling up your balloon with fuel. All right, yeah, keep going. Keep going. We could use a little bit more. Okay. Okay, yeah, now tape it on. Right, 2 pieces of tape, right? This is stuff you can do in your classroom, right? Yeah, you can take a round balloon, you can take a long skinny balloon, you can compare them. We don't have time to do that now, but you can try it out, see which one works best. Make an experiment out of it. All right, now, before we launch rockets, what do we have to do?
Have a countdown.
Have a countdown. So let's count down from 5, 4,
3,
2, 1. Let go. Oh, how sad. This is how you know it's live, people, right? So, right, you've seen the email, you've seen the phone number. Call us up, give us a little something, right? And let's go to Dr. Ann Spence to talk a little bit more about thrust. Ann?
Well, in the early days of rockets, even those fizzled sometimes, so it's okay. There's a couple other ways that we can use to have thrust on an aircraft. One of the ways is what Anarissa has here. What kind of engine do you have on your aircraft?
A turbo jet engine.
So there's a jet engine on this aircraft. That makes it go pretty fast. And now we have Gayatri. What kind of engines do you have on your aircraft?
Propellers.
Got propellers. Now the different thing about propellers is they're just kind of like little wings. They just act like little wings. They generate lift, except the lift is being generated in another direction, and it's actually pulling us through the air. I have a quick question from Tanner, a phone call from Tanner. What's your question? Tanner, are you there? I'm sorry?
Propeller airplane or a jet?
What was your question? Say it one more time.
What is safer to fly in, a jet or a propeller airplane?
What was the first part? I didn't hear it. What is safer to fly? What is safer to fly? Is that your question?
Yeah.
A propeller or a jet? Well, I don't know that there's really a whole lot of difference between the two. If you lose an engine in either one, you kind of lose an engine. You've got to somehow glide to the earth. So I don't know there's really much difference in safety. Okay. Thank you for calling from Arizona, Tanner. All right. We have any other questions? Any other phone calls now? Nope? Okay. Well, we've talked about the different kinds of thrust we can have. We can have propellers, we can have jet engines, and we also saw the rocket. Let's go over to John Anderson so he can tell us about another aircraft that uses rocket engines.
Okay, we're going to talk about supersonic flight. The students who are here, on the count of 3, I want you to give one loud clap. 1, 2, 3. Ah, what a noise. That noise was sound, and that sound propagated through this room at 760 miles an hour. That's the speed of sound. That's a lot faster than you want to drive down the highway. Whenever an airplane, such as this airplane right here, flies faster than the speed of sound, then it's called a supersonic airplane. This is the Bell X-1. This is the first airplane to have flown faster than the speed of sound. That was accomplished in October of 1947 with Captain Chuck Yeager as the pilot. We had a question earlier, by the way, as to what happens, why don't airplanes melt when they fly at the speed of sound? The answer is they don't melt at the speed of sound, but if they would fly at 20 times the speed of sound, they would melt because the temperatures would get so hot on the surface. We have a call from Ben in Minnesota. What's your question, Ben?
What do all the different gauges and knobs mean inside the cockpit?
Ah, that question would take hours to answer. But basically, all those gauges and knobs have to do with telling the pilot how the airplane is performing, how fast it's going, essentially how high it's flying. The knobs are there to control things like the throttle, the thrust of the engine, the attitude of the engine, the speed of the airplane, and so forth. So there are a lot of knobs and a lot of gauges. That's why pilots go to school for a long time to learn how to fly airplanes. One last thing I want to point out. We've been talking about airplanes, the shape of airplanes. This Bell X-1 is shaped very slender. Look at the fuselage and the wings. Very sharp, very slender. That's how you build supersonic airplanes. Now, we're going to wrap this up. We're going to go back to Blake.
All right, thanks a lot, Dr. John. Now, we did get a question earlier in the show. What is the newest airplane that we have in the museum? And we found the answer. The answer is the Voyager, the airplane that flew all the way around the world, right, on one tank of gas. That's the newest airplane that we got. What we have 4 students from Iowa City, Iowa, who are going to tell us a little bit about one of the projects that they did, which is going up in the Space Shuttle in June 2001. Everybody say hi to Nikki. Yeah, Nikki, why don't you introduce everybody in your group?
Okay, this is Sean, Joni, and Kevin.
Tell me a little bit about what's going on with your project.
Well, this is the imaging media experiment, and what we're doing is we're sending the different images on the different types of media into space to see what effect cosmic rays have on them.
All right, so what you're doing is you're sending different media, right, different ways of storing images, film, right, memory sticks for digital cameras, right, to see what effects cosmic rays have on it. Because if you're going to go into space and you're going to do experiments, you're going to need some way to store all that information, and you want a safe way to do it. Now, we want to thank you, everybody, for joining us today. We had a really good time bringing you this electronic field trip. If you are interested in the future, oh, wait, ooh, guess what? We have a question. Who's our question from? Robert from New York. What is your last question of the day? Oh, well, that's not a very... Oh, hey, we got Kevin from New York on the line. Kevin, what's your question? All right, so here's what we got. Later on in the year, if you liked what you saw here, right, we are live. This is very exciting for us. We hope it's exciting for you, where there are a lot of things that we could do electronic field trips on, right? We could do electronic field trips on supersonic flight, on space flight, on 2003. That is the 100th anniversary of the Wright brothers flight, right? And to commemorate that, the Air and Space Museum is building a brand new facility. Let's see if we can show you a little bit of video of it. Right? All right, so anyway, here's what we got. In 2003, we are building a brand new building, right, to store all of our leftovers. From everybody here at the National Air and Space Museum, thank you very much for joining us. Have yourself a good day. Bye-bye.
We're now at 13,000 feet, still 330 knots. We're doing pretty good. Okay, now here comes a crossover. I'm going in the afterburners. And what we do is pop up on the other side. You feel the acceleration there. There we go. Picture of the belly. Belly of the airplane there.